Hello everyone and welcome to Looking for Pythagoras 4.2. Our learning target for both 4.2 and 4.3 is I'll understand how to convert a rational number fraction to a decimal and then back to a fraction again. Our ACEs for 4.2 is going to be number 1, 3 through 10, and 24 through 31. So in 4.2, we want to be able to represent fractions as decimals. And then in 4.3, we're going to take decimals and turn them back into fractions. And it tells us here that rational numbers are numbers that you can express as ratios of integers. And another way to say ratio of integer is it can be numbers that can be written as a fraction. All right. Now, an example of these whole bunch of different fractions that we have down here, these are all rational numbers. Now, irrational number can't be written as a fraction. Okay, so that's a way to tell the difference between rational and irrational. If it can be written as a fraction or a, a, a terminating or repeating decimal, it's rational. If it can't, then it is irrational. Okay, you can read through this in the book or pause here and read through that. I'm going to jump down to this paragraph, and it says, in the examples below, you can see that sometimes the decimal representation terminates or ends after a limited number of digits. These decimals are terminating decimals. Like this one, it's terminating. It came to an end. There's nothing after this 5, okay? That's a terminating decimal. Sometimes a decimal representation has a repeating pattern of digits that never ends, and these are repeating decimals. A couple examples here, -7 divided by 3 equals 2.3333 forever and ever, okay? And then another repeating decimal, -1 and 3/7. Well, if we convert that, with 7 times a -1 is -7 plus our 3 is, we have our -10/7. And that becomes 1.428571. 428571. So the 428571 is the repeating part, and we'll continue to repeat that way forever. And it tells us that we can write a repeating decimal with a bar over the repeating digits like they've shown here for this one. We could also do this one here. Instead of writing a whole bunch of 3's, we could, let me put the negative there, -2.3, and just put a bar over the 3's, and that means that 3 is repeating forever and ever. Now, sometimes decimals don't terminate and they don't repeat. And a couple of examples here. These have a pattern, but they do not terminate or repeat. So we have 1.0100100001, so on and so forth here. And then we have 10.1112131415, so on and so forth. Now, if you take a look at the patterns here, what would be the next 4 digits in each string of digits? So if you need, think about this for a second, pause the video, that's okay. Decide what the next 4 would be. So in here, this pattern is going to continue, and the next 4 digits are going to be 1, 0, 0. Here, our pattern is 10.11, 12, 13, 14, and continuing on. So our next 4 digits here are going to be 29 and 30. Okay? So these are neither repeating or terminating decimals. They just have a pattern, and they will go on forever. So as we look at the problems here, part A just asks you to use a calculator to write a fraction as a decimal. Remember, this just means 2 divided by 5. Many times I get asked, how do I put fractions into the calculator? Well, you just do what it says, 2 divided by 5. That'll be your fraction. Part B, Jose and I have some different ideas about things. Do they agree? Do they not? And then it asks you to make a conjecture or a decision or come up with an idea or a theorem about how to predict when a fraction will have a terminating decimal representation. Okay. Part C, for each decimal, find 3 equivalent fractions if possible for 1, 2, and 3. Part D, I just want you doing number 2. Is it possible for a fraction to have a decimal equivalent that does not repeat and does not terminate? And that's it. And then again, our ACEs for 4.2 is 1, 3 through 10, and 24 through 31. Hope this is helpful. Look forward to seeing you in class. Good luck.